Okay, this presentation is on the electronic structure of atoms. Comes from chapter 6 in our textbook. And it's basically talking about electrons in an atom and where they're found and what we know about them and their energy levels and all that fun stuff. Before you can start talking about the electronic structure of atoms, though, we got to talk a little bit more about the nature of electromagnetic radiation. And to do that, we got to define a couple terms you're probably familiar with, but wavelength, basically the distance between corresponding points on adjacent waves. So it'd be distance between peaks or different distance between troughs is the wavelength, and that's is abbreviated with this Greek symbol lambda. And we also talk about frequency, the number of waves passing a given point per unit of time. So that's wave frequency. And then we talk about the electromagnetic spectrum. So basically all energy falls on this spectrum here. We've got visible light, which we're familiar with, and then with more energy, we got ultraviolet, X-rays, and gamma rays, and then infrared having less, microwaves having less, radio frequency having even less energy. And then, of course, the visible spectrum being broken down into good old Roy G. Biv, red, orange, yellow, green, blue, indigo, violet of the visible spectrum. And basically all electromagnetic radiation travels at the same velocity, which is the speed of light, c, approximately 3.00 times 10 to the 8 meters per second. So the speed of light equals wavelength times the frequency. The problem with this is the wave nature of light does not explain a couple sort of phenomena that we see in nature. The first one, black body radiation, is where the emission of light from hot objects glow, and the hotter they are, they glow at different temperatures. So you talk about like red hot versus white hot. The photoelectric effect, which is basically electrons are emitted from a metal surface when certain wavelengths of light are shined upon it. And then emission spectra, so light released from excited gas atoms don't have that nice rainbow spectrum that we saw in the previous slide. Instead, they have much smaller, more discrete spectra. So the first problem, the black body, was sort of explained by Max Planck. He kind of came up with this in 1901. And then he assumed that energy comes in packets called quanta. So that's why the black body radiation would start off maybe as orange, and as you pass a certain threshold, you jump to the next quanta of energy, and then it turns into a different color of light being emitted. So that's why it sort of corresponds to that. And a lot of people like to think of it as quanta being, like going up in steps, as opposed to walking up a straight, like an incline like that. And then Einstein used this to explain the photoelectric effect. So he said if you've got a stream of electrons coming in and hitting the metal surface and exciting the electrons, he figured out that the energy is proportional to the frequency. So energy has this Planck's constant in the frequency, and the Planck's constant is 6.626 times 10 to the negative 34 joule seconds. This is not something you need to memorize. This will be a quantity that's given to you on the AP exam in our tests and stuff. And then, so then if you know the wavelength of light, you can calculate the energy of one photon or packet of that light. So you've got the speed of light is the wavelength times the frequency, so the energy then equals that constant times the frequency. And then with the emission spectra, again, energy emitted by atoms and molecules have like a very discrete spectra. So instead of getting this continuous spectrum like we talked about before, you get a line spectrum. So if you're emitting or shining light through helium, this is what you get. Instead of getting Roy G. Biv, you get a little bit of that, And neon, you get more, but you still don't have this complete spectrum. And so Niels Bohr used Planck's assumptions, and Einstein's as well, and kind of explained the phenomena in this way. And so basically electrons in an atom can only occupy certain orbits, or orbitals, corresponding to certain energy levels. So if this is your ground state here, this is like the normal state, and then you can increase energy, and there's different levels, different orbits. And so you're allowed to be in certain orbits, and you have those allowed energies. And so then when you're in those orbits, the energy is not being radiated. The electron is keeping that energy. But if you excite an electron and move it up to another level, so it's in its excited state, when it comes back down, it emits energy. So it absorbs energy, it takes energy to make it go up there, and then when it comes back down, it releases energy. And so he's using that same equation with that explanation. And then Louis de Broglie sort of built upon that, and so, hey, if light can act like a wave or a stream, then maybe electrons can too. And he demonstrates this relationship, the relationship between mass and wavelength. So wavelength being the constant over mass times the frequency. So what the heck does all this mean? Why do we care? Well, basically, we see that we have this dual nature of matter, right? Matter can be a particle or it can be a wave. And so this really sort of throws us for a loop. So kind of limits what you know about an electron, because electrons waves can extend out into space, but then the position can't be precisely defined because they can extend out anywhere. And so we can't, you've probably heard this before, electrons' position and momentum at any given time cannot be simultaneously known. You can't figure out both of them. And so then, because of this, scientists began describing the probability of an electron's location instead. So really, it can be anywhere, but we're really likely to find it in this one spot here. And it's kind of neat. In many cases, our uncertainty of the whereabouts of an electron is greater than the size of the atom itself. So it could be outside of the atom, right? But kind of weird. So this leads to quantum mechanics. So Schrödinger, you've probably heard of him in Schrödinger's cat. He develops this mathematical model and uses both the wave and the particle nature of matter. And we call this quantum mechanics. And so basically this wave equation, which we're not really too concerned about knowing, designated with this lowercase Greek psi. And the square of the waves, psi squared, gives this density map, this probability of where you're going to find electrons. So you can see you're really likely to find an electron here is a high dot density. You're much less likely to find an electron way out here. And so using his mathematical equations, we came up with this set of orbitals and their corresponding energy. And so each of these orbitals describes a spatial distribution of electron density. So basically where you can find an electron. And all these orbitals are described by a set of quantum numbers. The principal quantum number is the one we worry about the most, and describes the energy level on which the orbital resides. There's also angular momentum, which defines the shape of the orbital. So a couple different shapes, or the shapes that we'll see, shapes S, P, D, and F. They'll become familiar to you. The magnetic quantum number describes the orientation of the orbital, and then the spin quantum number refers to the spin of the electrons. When we're talking about the principal quantum number, it's, like I said, describes the energy level on which the orbital resides, and basically they're in integers greater than or equal to 1. The other quantum numbers we don't really need to worry about. Certainly not calculating them or the actual numbers. We'll talk a little bit about the concepts behind them, but as far as quantum numbers are concerned, really all we care about for the AP exam is n, the principal quantum number. So it doesn't only tell you the energy level, but it also tells you the sublevels in a little bit of these shapes. You probably recognize these from just before. So the first energy level has 1 sublevel, the second energy level has 2, the third has 3, and so on and so forth. So to talk about those orbitals and what they look like. The s orbital is roughly spherical in shape. So this is where you're most likely to find the electrons. And the radius of the sphere increases with the value of n, obviously, right? As you have a second orbital, it gets bigger, and a third orbital gets even bigger still. If we look at a graph of the probabilities of where we find electrons versus distance from the nucleus, we see that in s orbitals, they possess an n-1 nodes, or regions where there is 0 probability of finding the electron. So if we're looking at something very simple like helium or hydrogen, 1s, right? There's 1 minus 1, there are 0 nodes. When you get something a little bit bigger, all right, you can see that there's a peak here and then a peak here. So there's 2 distinct regions where we're going to find where we expect to find electrons, and there's areas where we really don't expect to find them. And then consequently, in a third, the same thing. We've got two nodes. And it kind of looks like, or we think it looks like this, right? Different layers of these spheres. The p orbital, they have two lobes with a node in between them. So in cloud, we kind of should, in theory, it's this cloud format, but we tend to draw them like these balloons instead. And then there's the d orbitals. 4 of the 5 have these 4 lobes, so they look kind of like clovers, I guess, and the 5th one is this funny looking one, has a donut around the center. And we're not going to worry too much about the f orbitals. That's, again, beyond our scope. And as far as the energy levels go, for a 1 electron hydrogen atom, orbitals on the same energy level all have the same energy. That is, they're degenerate. So anything that has the same level of energy is degenerate. So this one is going to be. Just to orient ourselves to these shapes, each of these boxes represents 1 orbital. Each row is a shell. So we've got n equals 1, n equals 2, that's another shell, n equals 3 is the next shell, and then each cluster of boxes is a subshell. So S, P, and D. But as we increase the number of electrons, we also get repulsion between the electrons, right? Negatives repel other negatives. So in a many electron atom, there's no longer these degenerate levels. So now you still have the 1s, this one is still degenerate, but now you can see the energy levels are a little bit different. They don't have the same energy. The 2p has a little bit more energy than the 2s. The 3p has a little bit more energy than 3s. When you get to level 4, now we start throwing in the d, and we've got 4s, 3d, 4p. That was a little bit wacky, right? These guys, though, are still degenerate, these 3. So just like it says here, S has less energy than P, has less energy than D, which has less energy than F. And again, we're not going to worry about F too much. The last number, the spin quantum number, talk about it a little bit, but basically we figured out that no 2 electrons in the same orbit can have the exact same energy. So this led us to that spin number. So we found that, okay, you've had a little bit of a different spin, so that affects its energy. So yeah, that's the spin quantum number. And again, not really that important, but why do we need to know the spin, or why do we talk about the spin? It becomes important with the Pauli exclusion principle, in that no 2 electrons in the same atom can have exactly the same energy. So we find that the electrons actually will have different spins, and thus have slightly different energy levels. So yeah, electrons will not have the same spin. They can't have the same identical quantum numbers, so that small spin gives them different quantum numbers. This affects magnetism, so atoms are either paramagnetic or diamagnetic. Diamagnetic, all electrons are paired, the sublevels are full, and atoms are unaffected by a magnetic field. Versus paramagnetic, there's empty spaces, so some electrons are not paired, and therefore the atom is affected by a magnetic field. Orbital diagrams, basically, this is another way of representing what these electrons look like. And so in this case, each box in the diagram represents 1 orbital. You've got the 1s orbital, the 2s orbital. And the half arrows represent the electrons. And then the direction of the arrow represents the relative spin of the electron. So one spinning one way, one spinning the other. So they're spinning opposite from each other. The 2s orbital, in case of lithium, only has 1 electron in it. It's unpaired. For Hund's rule, the degenerate orbitals, the lowest energy is attained when the number of electrons with the same spin is maximized. Who cares, right? This becomes important when you talk about where the electrons are going. So as we move from element to element, how they get filled. So basically, because of Hund's rule, as you're moving from lithium to beryllium to boron to carbon to nitrogen, and you see you're adding electrons. So we've got 1 electron in the 2s, and then it's going to add here. I'm going to fill up the 2s. Now we're going to start moving to the 2p. You get our 1 electron. And the second electron, instead of being in this same box, be like, no. I'd rather be over here so we can maximize the number of electrons with the same spin. Because if it was in this box, it would have to be, if it was in this box, it would have to be an arrow pointing down. And then nitrogen, the same thing. And then obviously as we were to keep moving over, oxygen then would dump an electron here, and then fluorine would dump an electron here, and then neon, now we're all full. Okay. So we fill the orbitals in increasing order of energy. So if we're moving across the periodic table, 1s, then we fill this 1s over here, then the 2s, 2p, 3s, 3p. And it all makes sense until you start to get to the level 4. Then you got 4s, and instead of going to 4p, remember we were showing that diagram way back a little bit ago, the 3d actually has more, is the next level of energy. So then we go 3d to 4p. So you can see here 1s, 2s, 2p, 3s, 3p, 4s. This is the way that we fill the electrons. In these different blocks on the periodic table, again, correspond to those different types of orbitals. Remember, you got the s orbital, which is the sphere, the p, which is like the two balloons tied together, the d orbital, which is like the clover. And then when we're looking at valence electrons, so these are the outer electrons, we're only going to look at the s and the p blocks. The d electrons are not valence electrons. So when you're counting up how many outer electrons they have, you'll be looking at the s and the p. That's it. So this becomes important when we're talking about electron configurations. So you can basically designate where all of the electrons are in an atom. So we have, this term shows the distribution of all the electrons. So each has a number. So this is the energy level. So this is the 4th energy level. The letter shows the orbital, and then the superscript shows the number of electrons that are in those orbitals. So when we're looking at the electron configurations, there's two options, the full configuration or the noble gas configuration. So if we're going to look at neon, right over here, this is basically how electrons would fill in. They would go to the 1s level first. So there's 1, the s first, s1, s2, and then we go down here to the 2s1, 2s2. So there's where we get our 2s2, and then we move over to 2p, 1, 2, 3, 4, 5, 6. There's neon for you. 1s2, 2s2, 2p6. Neon is a noble gas, so its configuration would obviously be the same. If we're going to look at sodium, which is just one level down, it's basically going to be the same as what neon was, because they're going to fill in the same way. 1s2, 2s2, 2p6, and then we move down to here to 3, 1, 2, 3. We're in the s block, and we're the first one, 3s1. So you can write out the full configuration. Or you can take a little cheat and say, well, it's neon plus this. So you can sort of back up to the previous noble gas and say, all right, neon, and then the little bit extra, which is the 2s1. It's kind of a shortcut way of doing that. So for example, the electron configuration for chromium is argon 4s1 3d5. You'd expect it to be 4s2 3d4, right? Because of where it is, 4s2 1 2, and then 3d4 1 2 3 4. But it's not. It's 4s1 3d5. This happens because the 4s and the 3d energy levels are really close to each other, and so sometimes they can kind of be a little bit interchangeable. So in this case, the S2 was a little bit happier in that D instead. They happen down here as well, but again, we're not too worried.